All right, let's see if we can write the equations for the piecewise functions that are here. If you look at 35 here, uh, first you want to get where the partial domain is. So you see there at 0. And when we're dealing with 0, we can use less than or equal to 0, or you could use less than. So let's go ahead and graph this one. We want to identify this. We see the y-intercepts at 0, so this is going to be just something times x for the first one. So we write our piecewise function. We use the brace. There's only two of them, so we just need two rows. The first one is going to be x is less than 0, and for the second one, x is going to be greater than 0. All right, so for the first one, let's just use, we know it's something x. There's no y-intercept. The y-intercept's at 0. So it's not plus anything or subtract anything. It's just mx. So what is our slope? We can just count that from anywhere. That's up 1. It's up 1 over 1, up 1 over 1. And what does that? 1 over 1, just x. And so that's our first part. Then the second part, you can see it's steeper there. Once again, there's no y-intercept. So we can count from there till we get to a nice easy cross point. That's 1, up 1, 2, over 1, 2x. And there you have it. Number 35, that's our step, our piecewise function. So we have f of x is equal to, we have three of them there. For the first one, you see that it's including 1. So it's greater than or equal to 1, the x. And I'm just erase number 36 to get number 37 in there. So it's greater than or equal to 1, but strictly less than, because it's an open circle there. Strictly less than, what's that, 2? The second domain is equal to 2, but greater than as well. And that's 2, 3, 4, strictly less than 4. And the last one begins at 4, so x is greater than or equal to 4, but it's going to be strictly less than 4, 5, 6. And so that's our domains, and now we just need to say what those constant values are. That's 1, 2, that's 2, 3, 4, and 5. So we just have 1, 3, and 5 that's being used. So 1, 3, 5, and done. And that's your piecewise function for number 36, sorry. Okay, so let's go ahead now and try number 37. And I might be able to fit 37 in that little area. So number 37 here, make it light blue. And it's only two functions, so we don't need that much space, hopefully. Let's see if I can fit that in there. First, you want to identify your domain. You see here that's negative 1. So one side is strictly less than negative 1. So x is less than negative 1. And hopefully you can make that out. X less than negative 1. And then over this side, it's going to be x is greater than or equal to, because of the solid dot, negative 1. All right, so x is greater than or equal to negative 1. All right, now we just need to go and figure out what these equations are. Now you're going to have to use your understanding. I'm trying to get back to this light blue. You can see from the slope where the intercept might be. If you count here, you'll notice that this line is going up from here. It's going up 1, 2 units, 3 units. So 3 units up, right here, right? 3 units up, and then 2 units over. So that's the slope for that one. And it's 3 over 2. 3 over 2x. And now you need the intercept. It's a positive intercept. Now you can see it's going to go a little bit higher than this. It's going to be up here somewhere. That it's going to be, this is about 4. Right, that's about 4, and it's going to go, this is 5. It's going to be about halfway there. So halfway in between there will be 4.5. Now, because it's already written in decimal fraction form, instead of writing 4.5 or 4.5 in decimal form, we can just rewrite that as a mixed number. Remember, multiply. 2 times 4 is 8, plus that becomes 9 over 2. That's the way we keep it consistent. So we have 9 over 2. And then the second one there, the second part of that, you see that's negative 1. And so that's just a straight line across, so just -1. And that's our function. All right, so example 5 is referring to a piecewise function in real life. And so for this one, we're going to write and graph a piecewise function for the parking changes shown on the sign. Now, this is from your example. This is a good one here. And it's telling you that it's a step function. So sometimes you have to just figure that out from the question. So part A says write and graph a piecewise function for the parking charges shown on the sign. So the sign says garage rates for the weekends, $3 per half hour. And then it says $8 maximum for 12 hours. All right, so let's write out our function for this one. We have f of x is equal to, and let's just put a brace there. Now how this sign works is saying that it's $3 per half an hour. Once you get to $8, it's just that for a maximum of 12 hours. So that means that at a certain time, you just switch over to 8. So let's start off with the first one. It's $3 first. Our time, which we could represent by x or t, is up to you. So we have 0, and we're going to be greater than 0. And that's our time or x value. And that's going to be less than or equal to, it's per half hour, so 0.5. That's half of 1 hour. So then after that is another $3. So if we went another half, that would be $6. And we're starting at 0.5, but not including it for this part. So it's just when you go over, so we had 31 minutes, so it's strictly greater than. And then it's ending at the next half hour, which would be 1 for 1 hour. Now, if it's at $3, that's 9. So instead of paying $9, you pay 8. And so $8. And so assuming you get to an hour, that's when you could just pay $8 for the maximum amount of time, which would be greater than 1, but less than or equal to the total maximum, which is 12 hours. So we have our piecewise function, and we could go ahead and graph that. First, you want to look at your domain. You're going to 12, but then you have a half there. So you could use what we call a break to help us there. We could start off with the first few and then have a break in our axis. So we can do something like this. Once we get to a certain point, we can do our little break here and continue. And we put t there. I'm going to change this to a $sign. I know it's f of x, but we can write a $sign just so that it stands out. So we have here, we're going to skip 1, 2, 3, and then instead of 4 there, we're going to skip, and this would be, let's say 10, 11, 12, 13, etc. And then here, we're going up to about 8. So can I go by 2s? 2. Should have went down. One more. 2, 4, 6, 8. So I could go by 2s. 1, 2, 3, 4, 5, 6, 7, 8. Notice I wouldn't fit it there if I went by 2s. Alright, so we can go ahead and graph these now. For the first one, it's 3, and that 3 stays the same from 0 to 0.5. So open circle at 0, solid circle at 1.5. Straight line. And then at 0.5 it goes up to 6, so it's an open circle there. And a solid dot at 1. And then at 1 it's an open circle at 8, and this time it goes on for a long time. And close circle. Alright, and that's our step function in real life, so we can have a visual graphic on that. Alright, so for example 6, this says during a 9-hour snowstorm, so this is the total amount of time, it snows at a rate of 1 inch per hour for the first 2 hours, at a rate of 2 inches per hour for the next 6 hours, at a rate of 1 inch per hour for the final hour. Number 58 wants you to write and graph a piecewise function that gives the depth of snow during the snowstorm. And then number 59, how many inches of snow accumulated from the storm. Number 59, you could probably just do that in your head, but they do want you to have a piecewise function shown and graphed. So let's go ahead and do this one. These ones could be tricky at first, so you have to be careful that you're making sure everything works. All right, so we know we're going to have f of x equals to, I think it was about 3 different scenarios there. The first one is 1 inch per hour. You could represent time to be a variable. We're going to be starting here at 0. So 0 would be our time, and we're going to use less than or greater than or equal to here. We could use x. I put x in there. Or we could use t for time. To be consistent, I'll put t since we're dealing with a real situation and fix that to a t. All right, that looks horrible, so we want to make sure that looks good. So we have f of t for time. And then the first set of time is going to stop at 2 hours. All right, so what would be our variable there? If it's 1 inch per hour and t represents hours, that's 1 times t, which could just be written as t. So we have t when our time is between 0 and 2. All right, then we move on to the next one, which is 2 inches per hour. 2 inches per hour for the next 6 hours. Now we have to be careful here. What we have so far is that it was snowing at a rate of 2 inches per hour. So in the first hour, 2 inches of snow has accumulated. And then it's 2 inches per hour for the next 6 hours. That's going to be a total of 12 inches. Right? So that was the first 2 hours, and this is the second 2 hours. Now, what we have to be careful on is that here, if I put 2t here, and as you remember with the piecewise function, my next set of time starts at 2, but it's strictly greater than 2 here. And it's going for 6 hours. 6 plus 2 is 8. If I was to substitute 2 in there, I have 2t times 2 is 4, right? 2, if I substitute 2 in, I'll have 4. Now, that's not highly accurate because I'm not starting, if I'm saying I have 4 inches of snow already at the second one, that's not true. What I'm really starting at is I'm starting at where 2 is. And so I have to actually subtract 2. For instance, uh, let's say I had 4 inches of snow. That's not 4 inches of snow at 3 hours, right? What happens is I'm going to have to take away the 2 inches of snow that is already there. And so I'm going to have to subtract 2 in order to make this work out correctly. So for instance, the first 2 hours, if we wrote this on the side, I have 2. Now if I substitute the 2 in there, I have 2 times 2 is 4, and 4 subtract 2 is 2. I actually have 2 inches in the first hour, and then 2 inches in the second. So that's the only way I can get the accurate reading of 2 is by subtracting 2 from that. I'm going to have to do the same thing here. And so I want to first of all write out what my domain is. I'm picking up at 8, and it's going to be strictly greater than 8. And that's for 1 more hour, so that's going to be less than or equal to 9. Now remember, this is a rate of 1 inch, so that's 1t, or just t by itself. But if I substitute t, the first t in there, 8, into there, that's 8. And that's not going to be working out well because here, if we used to substitute this in there, the last part of this, 8 times 2t is, let me do it on the side so it really stands out. If I was to substitute the last part of that domain, partial domain, 2 times 8 subtract 2, what I would get is 14. Now if I substitute this 8 into here, I get 8. So that's a problem. This has to pick up where the 14 left off. And so what we need to do is just add the difference that will get me to 14, which would be 6. So t plus 6 gets me to the 14. And so now, if I was to substitute 8 into there, 8 plus 6 equals 14. We did the same thing with the second step. And so now we have our piecewise function. And if you substitute them in there, you see how it will work if you do each one. All right, so now that we have the actual function, we can go about graphing it. All right, so let me just make sure we identify what this function looks like. what you'll notice is that we need to go at least to 9 in our t-axis, and in our inches, which could be f of t, we're going to have to go up. We can always check it by just saying 9 into this, so 15. 9 plus 6 is 15, so we need to go up as high as 15 there. Alright, so let's go ahead and graph that. And I'm looking at our equation as well, our expression. I want to have -2 to be if I use the slope-intercept form. You can use your a table to help you out as well. And I'm just going to space it out still just to make it look neater. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we're just going to make 15 work up here. 15. All right, and then here we can go by ones again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For this, we could use a table, or we could use slope-intercept form. If we use a table, we're just simply trying to find the starting and beginning points. So for the first one, if we substitute 0 into there, right, when t is equal to 0, y is equal to 0. So we know the first point is there with the solid. And then if we substitute 2 in there, then y is 2. So this is where the other one is with a solid circle. So we can just connect that. The second one, we substitute 2 in there. 2 times 2, subtract 2. It's going to give us 4 minus 2, which is 2. Exactly what we wanted. So when 2 is there, 2 is there, and we're starting at the same point. And then we could just substitute 8 into that same part of the function. 2 times 8, subtract 2. That's 16, subtract 2, which is 14. So we go over to 8, and we're going to have 14 there. And so we scroll up to 14, and that's a closed circle. And we could just connect those two. And then the last one, if we substitute 8 in there, 8 plus 6 is 14, which we should get. But because of the type of line, we don't have to worry about it. We substitute 9 in there. 9 plus 6 is 15. And so we go to 9. And that's a closed circle at 9 as well. And just connect those two. And we're done. And that's it. Just make sure you use a ruler, though, as it's more difficult for me to do so.